Hello everyone, my name is Hayden. I come from the University of Queensland in Brisbane, Australia, and today I would like to talk to you about my experiences of using Julia as a teaching tool to teach statistics to several hundred students studying at UQ. Okay, so for a bit of context, one of the larger courses taught in the UQ School of Maths and Physics is the statistics course Stat 2201. It's primarily a service course in statistics for second year bachelor students studying various types of engineering. It typically has between about 400 and 500 students, and because the audience is quite broad, many of the students have limited programming and mathematical knowledge. The course itself had been around for many years, and it was showing its age quite badly. So at the start of 2017, Dr. Yoni Nazarathy and myself, we rewrote the course from the ground up with new content, assignments, final exam, etc. So the main aim of the course is to cover foundational statistics and probability, and also to provide some introduction to programming. And in the past, the course had used Minitab, but since we wanted to make it more exciting, we used Julia for the rework. And the reason we chose Julia was because it has a very elegant syntax, which is easy to learn and code in. There were various packages that existed and functions that we needed for the coursework, and also because it's fast to code in Julia and it has fast runtimes. So then our main concern was how to roll Julia out to our 400 odd students in the easiest way possible. And rather than rely on students setting up their own local installations, after contacting Julia Computing, we decided to go with JuliaBox. So they set up a section on JuliaBox for us where all our students could go and log in, and it came pre-configured with all the packages required to do the coursework. And the reason that we chose JuliaBox was because the students themselves, because they didn't have a lot of knowledge, we didn't want to risk having hundreds of students coming to us and asking us for questions regarding their own setups and things like that. So to give you some perspective, the largest class at the time that was using Julia, I think, was only a dozen or so students, or 24 students. So to go from that to 400, 500 students, it presented quite a risk. So since many of the students had never used Julia before, we also provided them with a sort of a cheat sheet of the main functions that they would need for the coursework, and we didn't want to bombard them with too much information, so we just summarized essentially as much as we could onto a single page. And you'll notice that many of the functions come from the stats-based distributions, hypothesis tests, and GLM packages. Now, in terms of assessment for the course, there were 5 assignments and a written final exam. And for each of the assignments, the students were required to use Julia to solve a series of probability and statistics-based questions. And once completed, they would simply save their JuliaBox notebooks as PDFs and submit them electronically for marking, helping the environment in the process. And overall, the process went pretty well. There weren't any big hiccups or issues. The adoption of Julia worked quite successfully. There were some issues with students having problems logging in at the very start, but that was mainly due to them not using the right emails or passwords for signing up. From the user perspective, because everything was cloud-based, it was very flexible for the students. So they could work both in the labs and also off campus. As long as they had an internet connection, they could access their files. There were some issues though. So we noticed that a large majority of the cohort would log in the last day that the assignment was due, and they would all try and do it in the last few hours, and this resulted in a noticeable slowdown of JuliaBox. And this could be easily mitigated in the future by simply staggering the due dates by the 2 lecture streams that we had going. The other thing was students reported intermittent random crashing and kernels dying throughout the semester. Although I personally didn't see much of this, so it's a bit hard to comment on that. And interestingly enough, in 2018, this happened again when Julia was 0.6. But I should point out that in both cases, both years, the support from Julia Computing was really excellent. Okay, so this leads me into my second topic that I'd like to talk about. So currently there are a few books out there on Julia, such as Mastering Julia, Julia for Data Science, and Julia for Operations Research, to name a few. But there's currently no book out there which combines Julia and statistics and probability in a sort of a holistic applied sense. So after we noticed this, myself and Yoni, we started working on our own book entitled Exploring Julia, a Statistical Primer. Now we've progressed it quite far and we're aiming to have it completed probably at the end of this year. It's broken up into the 10 chapters that you see here and begins with an introduction to Julia and probability, and then moves on to fairly rudimentary data cleaning and processing, then statistical inference, confidence intervals, hypothesis testing, and some modeling, and finally touches on concepts such as queuing theory, discrete event simulation, network reliability, and things like that. So as you can tell, it covers many different concepts, and it has over 100 standalone coded examples in Julia, of which you can find on my GitHub page. I've included 2 example code blocks here, along with a few illustrations from the book. So the first example on the top left is one on confidence intervals, and essentially calculates the lower and upper values for a series of observations and generates the attached illustration, and from that the reader can gain an intuitive understanding of what a confidence interval is all about. The second example below is one on the receiver operating curve and plots several different receiver operating curves for different alternative hypotheses, and the takeaway message from that is essentially as the difference between the null and alternative hypotheses becomes greater and greater, the statistical power of the test greatly increases. And I've included a couple of other examples on the right, such as a cumulative moving average of observations from a Cauchy distributed random variable in the middle left, an example of Simpsons Paradox on the bottom right, and one on common random numbers on the top left. So the book is primarily an introduction to statistics and probability, but throughout we try and focus on some of the more interesting examples out there, such as the Monty Hall problem, various occupancy problems, as well as others. Each problem starts with a discussion about the problem, followed by some mathematical setup, standalone Julia code block with output, and then some discussion about the code. Now, because it's aimed at sort of introductory end users, we don't really sort of delve deeply into a lot of the internals of Julia or discuss, user-defined types or global versus local scope in any big way, because that's not really sort of our aim, but rather our aim is to convey understanding of the many concepts that we cover through the use of Julia as a functional tool. And arguably, this is one of the strongest aspects of Julia, that an end user coming in doesn't need to be aware of many of these features to write sort of fast code, but rather Julia is fairly robust and works well straight out of the box. Okay, so as a final quick example here, because we're running out of time, imagine that we have a series of observations from some unknown underlying gamma process. Now, if we wanted to estimate the parameters alpha and lambda, one way we could do this is by a maximum likelihood estimation, and numerically try various combinations of alphas and lambdas until we find a maximizer for the likelihood function L in the second line here. And Julia is perfectly suited to this sort of numerical computation task given its speed. But this example here is slightly different. Obviously, it's an optimization problem, and it turns out that we can't find an explicit expression for the maximizer of L here. But by looking at the log likelihood and performing some algebraic manipulation, which we cover in the book but not here, we can find that the maximizer must satisfy the last equation shown here, which is a function of alpha and the sample observations. So what this example does, it generates a whole lot of different groups of sampled observations for observation sizes of 10, 100, and 1,000. And in lines 9 to 12 there, we create our own user-defined function MLE and use the F0 function from the roots package to solve that equation. And then we simply plot the corresponding alpha and lambda values. And what we observe here is that as the sample sizes grow, the distribution of the MLE asymptotically converges to that of a multivariate normal distribution, and that's exactly what we see here in the green dots here. So I think we're out of time. So thank you very much.
So one question: are you planning to update all your code examples for 1.0 before you publish?
Correct. Absolutely.
Are you covering Bayesian statistics as well in that course and/or your book?
Good question. You have to draw the line somewhere, I suppose. So unfortunately, the answer is no.
So I was just curious about what kind of feedback you were getting from the students. Did they appreciate having to learn Julia?
It was a bit of a mixed bag. So some of the students really liked it. Some asked why Julia and not Python. And my experience with Python is, personally, I much prefer Julia. And it may just be because some of the students actually hadn't sort of gone much deeper. I think, if people start actually really functionally using Python versus Julia, people may tend to like one more than the other. But yeah, it was a bit of a mixed bag.
Okay, let's thank Hayden again.
Thank you.